Um, so matter is a pretty simple concept, right? Um, First, we need to realize that we separate matter into two different categories. We have our pure substances, and then we have our mixtures, right? Um, then those can be further separated, and uh, mixtures are separated into either homogeneous mixtures and heterogeneous mixtures, and pure substances are separated into elements or compounds, right? Elements or compounds. So let's talk about each one of these, individually. When you're talking about a single element, right? Like for example, this penny right here, it's made of copper atoms. So uh, one type of atom is what we consider a pure element, right? It consists of one type of atom. Yep. So compounds, though, like water here, water is definitely a chemical compound. Um, it's made of course, oxygen and two waters. It looks like that. Sorry, oxygen and two hydrogens, rather. All right. Uh, so what that basically means, then, what is a compound? A compound is actually two elements or atoms that are chemically combined with each other. Chemically combined with each other. Combined with each other. Right. So that's a compound. Right. And again, pure substance can be either elements or atoms and compounds. Over the mixtures, right? Over the mixtures, a homogeneous mixture is a mixture where all the different parts of the mixture, you can't differentiate them. You can't distinguish them. They're indistinguishable from each other. So it looks like it's all the same thing, right? Um, Generally, that's because it's so small you can't tell the difference, right? The molecules or the particles are so small you can't tell the difference. So here you have is that a baritone or tuba? It's been a long time since I've been in band. Anyway, we have a brass instrument that's made of brass, right? And brass is actually a combination of copper and zinc, right? And they are actually a chemical mixture together, right? A chemical mixture, um, and of two elements, right? A chemical mixture of two elements, and you can't differentiate between the copper or the zinc components, right? And that's why we call it a homogeneous. Whereas a heterogeneous mixture, like this one here, is you can't even tell what that is. But I will go ahead and tell you that. You know what? Let me go ahead and just close me down real quick so you can see this picture. There we go. It's actually a cup of water, right, with some pennies at the bottom. That's definitely a heterogeneous mixture because you can tell the part that's water and the parts that's a penny. So that's a heterogeneous mixture. Interesting. I'm gonna come back to the screen now. So let's talk about the physical states of matter, right? Um, in talking about physical states of matter, we already know from grade school and primary school, high school, that kind of thing, that matter can be in solid form, liquid form, or gaseous form. Things to note, though, is that is that solids actually have a definite shape, whereas liquids and uh, gases take the shape of their container. In volume, though, both solids and liquids have definite volume, right? But gases fill the container that they are in, right? The arrangement of the molecules or the particles in solids are very fixed and very close to each other. In fact, they are moving very slow. They vibrate very slow. But in liquids, right, they're random. They're still close, but they're a little further away than they are when they're in solids. But they're still they're random. They're still very close. The speed that they're moving though is very moderate. So in the mediums between. Gases, though, they're super far apart, and the molecules and gases are spread out everywhere. That's why a helium balloon can just, fill up a balloon and just keep on expanding, because gases just expand, right? Very fast movement. Uh, Strong, very strong interaction between solid molecules. There's strong, just moderately strong, or just strong, but there's essentially none in gases. That's another reason why they can expand to fill their spaces, because since there's virtually no interaction between those gas molecules, they don't hold each other together, they don't pull each other together, they just kind of expand. So some examples here, water vapor and helium, air, they're all gases, right? And you see here our example of the balloon. Um, Water, oil, and vinegar, all liquids. You can see that there. The interesting thing here is that we have salt and a picture of salt. Funny, not table salt, but this is actually a geode. Geode, not a geode. There we go. Geode of something called am. Sorry, I can't remember how to spell this. Let me see here. There it is. See, I already spelled it wrong. Amethyst. Amethyst, right? Silicon dioxide. The silicon dioxide is actually what makes this geode purple. So that's pretty cool. That's neat. So when we talk about the states of matter, we can then discuss the changes that they go through, right? Or their properties, both physical and chemical, and the changes that they can go through. So these are just two very simple charts that will help you decide whether or not something has a chemical property or a physical property, and whether something is a physical change or a chemical change, right? So just briefly, if we have a physical properties are just things like color, shape, odor, luster, size, melting point, and density. Luster is just how shiny something is, by the way, like a metal. And chemical properties are their ability to interact with things. For example, also paper can burn, or iron can rust. So things that they can do, they're capable of doing or reacting with things. Silver can tarnish, right? So just translating that over to a chemical change, or changes in both of these properties. Physical changes are things that are like changes in size or the state of matter or its shape, but they're still the same molecule, right? Whereas a chemical change are things like I already discussed, how paper burns. Paper is getting burned. It's an oxidation reaction. Paper is a fuel, right? Iron rust. Iron is also being oxidized, right? That's another oxidation reaction. That's why we get iron oxide from iron when in the rusting process. And silver tarnishes, right? So these are just a few more examples right here. We already talked about water boiling before. That's a physical change, right? But when it comes to metals, right, uh, reacts with oxygen in the air, right, and that makes it tarnish or it makes it rust and stuff like that. So that's a chemical change. Copper that's being drawn into wires, that's definitely a physical change, right? Because it's still the copper. Uh, it's still the copper element in there, copper atom in there. Not changing that at all. Wood burning, just like paper burning, right? That's a chemical reaction. Here's an interesting one. When you dissolve sugar into water, right, it's actually staying sugar. It's just dissolved into water, because when you evaporate the sugar or try to remove the sugar from the water, it's still chemically still sugar. But if you heat up the sugar enough, right, it actually starts to turn into caramel, and that's a chemical process. Cutting paper into tiny pieces, that's into confetti, that's definitely a physical change. And we already talked about how iron can rust because it forms iron oxide with the oxygen in the air.